let's. Okay, so it's my great pleasure to introduce Andreas Fichtner tonight from ETH Zurich. First of all, I would like to thank for accepting our invitation for this midnight lecture with European time. So we very much appreciate it. So Andreas and I, we have known each other since our PhDs, and I can very confidently say that he's one of the brightest geophysicists of my generation, actually. So Andreas, very broadly speaking, is a theoretical and computational seismologist, mainly focusing on wave propagation and inverse theory at all scales, from medical imaging to global scale full waveform inversion, uncertainty quantifications, and recently I know that his interest is also in distributed acoustic sensors to collect data from urban areas. So Andreas received his bachelor degree from University of Mining and Technology in Freiburg in Eastern Germany. I just learned it today that Freiburg is very similar to School of Mines. It's a mining university. And what is interesting is that it has the first geophysics department established in the world. Following his bachelor studies, he was a Fulbright student at the University of Washington, Seattle. And then he did his master and PhD studies in Munich under the supervision of Heiner Riegel. Then he was a postdoctoral researcher in Utrecht. And after 3 years, he accepted a faculty position in Zurich, and he has been a professor leading the Seismology and Wave Physics group at ETH Zurich since 2013. So Andreas received many honors and awards, including Kate Aki Young Scientist Award by the American Geophysical Union in 2011, Early Career Scientist Award by the International Union of Geodesy and Geophysics in 2015. He received Hoffman Prize from Bavarian Academy of Sciences in 2018. I'm not going to count all of them, but what is interesting here is that he gave an invited talk at the 58th meeting of Nobel laureates in physics in 2008, which is kind of interesting for me. He published 5 books instead of what he told us in his bio, 4 books. I believe he forgot to add the last book that he published with Brian Kennett. But again, what is interesting is that I believe many of you don't know that he published his first book, which was about vector analysis when he was still an undergrad student in Freiburg. And he has many students, many talented students, postdocs. Actually, he's working with an army of researchers. And some of them are also our guests tonight. Whoever couldn't sleep tonight joined us. We welcome them as well. And it's my pleasure to give the word to Andreas to talk about uncertainty quantification for large-scale nonlinear inverse problems, basically one of his recent favorite subjects, Hamiltonian Nullspace shuttles for both probabilistic and deterministic problems. Thanks, Andreas.
Thank you very much, Ebu. Thank you very much for the invitation, for the opportunity to present our work. And there are 2 things I want to highlight already here on the title slide. The first is that this is work done together with my collaborators, Andrea Zunino, who is now also at ETH, and my PhD student, Lars Gebrandt. And also that even though many of the developments that I will show are very general and applicable to many different inverse problems, not only in geophysics, you will see that most of the examples and most of the intuition that I will show actually comes from seismic tomography, which is the application that I know best. A little bit about the motivation behind that work. I think it is obvious to everybody that, that during the past couple of years or past couple of decades even, the emergence of faster and faster supercomputers combined with improved numerical methods to solve, for example, the wave equation or other partial differential equations has enabled us to properly account for many complications in forward and inverse problems. For example, in a seismological context, the modeling of wave propagation through 3D complex models of the Earth or other inaccessible bodies, finite frequency sensitivity of our observations with respect to 3D structure, but also the nonlinear dependence of the observations that we can make, for example, at the surface of the Earth, on the model parameters that we would like to constrain, such as velocities, attenuation, and many others. So this is fantastic and really has led to many advances, to many applications. But there's actually an interesting and somewhat paradoxical downside of all of those developments. And that is, even though our computers become faster and numerical methods improve and we can account for all those complications, actually our ability to properly quantify uncertainties, the uncertainties of our inferences, has been reduced. Also because the very well developed machinery for nonlinear inverse problems, of course, tends to fail when we get into a nonlinear regime. Along the same lines, also our ability to actually find alternative models, for example, of the Earth that explain our data equally well, has become smaller. And as a consequence, also our ability to interpret tomographic Earth models may not come with a confidence that is as high as we would like. So based on this statement, on this motivation, this talk essentially has three main goals. The first one is to introduce an efficient method that allows us to produce alternative Earth models that explain our data equally well without Monte Carlo sampling. Based on this, I will still introduce a new Monte Carlo method that enables an even more comprehensive uncertainty quantification for large and potentially nonlinear inverse problems. This Monte Carlo method that I will talk about has the benefit of being very tunable. It has many tuning parameters that allow it to be potentially very efficient. But it also means that all of those tuning parameters actually have to be found in a suitable way that usually can't be done manually because there are too many of them. And so we have been thinking about ways to automate this. And this leads to the third goal, which is the development of an automatic tuning method for Monte Carlo sampling that works on the fly, basically while it is sampling. And this rests on quasi-Newton methods, well known from nonlinear optimization. So those goals, they translate into the outline of my talk. The first part will be on nonlinear null-space shuttles. The second on Hamiltonian Monte Carlo or Hamiltonian Monte Carlo tomography in the specific seismological context. And the third part on autotuning. So let's go. Part one, nonlinear null-space shuttles. We will start with a little bit of preparation and a hopefully clear problem statement. The first thing that we need to define, that we need to consider, is the so-called effective null space. To define this effective null space, we consider a misfit functional chi that depends on some model M. So chi may be some misfit functional that we find suitable, and M is some model, for example, of the Earth. And we assume that by some means, for example, through nonlinear optimization or maybe through a random guess, we have found an Earth model M hat that is acceptable, meaning that it produces a misfit that we find reasonably small. Now, the effective null space now is the collection of all of those models, M hat, plus some little perturbation, delta M, not necessarily little perturbation, some perturbation, delta M, that produce a misfit that is equal or smaller than the misfit of the acceptable model, plus some little misfit tolerance epsilon. And so that means we try to find alternative models that may have a misfit that is just a little bit smaller or somewhat smaller than the misfit of the acceptable model that we found in the first place. Now, the problem, of course, is how do we actually construct such models? How do we construct models that lie within the effective null space? Meaning, how do we construct models that are equally plausible than the model that we found in the first place? Why is this relevant? Well, first, obviously, for uncertainty analysis. What we would like to know is if the alternative models that we can find are actually drastically different from the model that we found first. If those differences between plausible models are very large, it basically means that our constraints are very weak and that we may not know very much about the medium that we would like to study. But also seen from the other direction, we may use this constructively. We may actually want to add, for example, some geological feature to an already existing model. And we would like to know how much of that feature can we actually add such that our misfit remains within acceptable bounds. So how does this work? The idea is in principle very simple. There's a trick, and here comes part one. What we do is we interpret a model, for example, a model of the Earth, as the position, say, of a space shuttle or of some particle in a high dimension. So for example, if our model space dimension is 1,000, then we consider a 1,000 dimensional position vector in model space, and we may intuitively attach to that position vector a space shuttle, a model space shuttle that is located at that position. Now we assign to that space shuttle a potential energy. That potential energy in a way is artificial. Right? The space shuttle itself is an imaginary thing, but still we assign it a potential energy, U, which depends on the position M or on the model M. And we say that that potential energy is equal to the misfit of that model. Right? So potential energy equals misfit. Now that we have a potential energy, we also want a kinetic energy. And the first thing we need for kinetic energy is some momentum. Of course, as I said, this space shuttle is an imaginary thing. So we plainly have to invent an artificial momentum. So let's call this P. It's invented, it's an artificial momentum. It's an auxiliary variable in the end. And based on that momentum that we just defined, that we just invented, we can compute a kinetic energy, which is simply 1/2 momentum transposed times the inverse of a mass matrix times P. So the mass matrix is the high dimensional mass of that imaginary space shuttle at position M. Now, let's make this momentum a little bit more precise. So far it was invented, it was completely arbitrary, but now we add the constraint that we would like to choose the initial momentum of the space shuttle such that it produces a kinetic energy. So the kinetic energy depends on the momentum. This initial momentum is P hat, and we request that the initial kinetic energy is equal to that misfit tolerance that we considered before in the definition of the effective null space. So this constrains, if you will, the length of the momentum vector, but not its direction. Now we have a potential energy equal to the misfit, a kinetic energy, and that allows us to define a total energy or the Hamiltonian H, which is simply the sum of kinetic and potential energy. So far, so good. Now comes part two of the trick. We don't want the shuttle to be a stationary thing. We want it to fly through model space. And what we do for this, we take Hamilton's equations from classical mechanics, and they're written here. So the time derivative of the model, so our model in model space suddenly becomes a time-dependent quantity. This is equal to the derivative of the Hamiltonian, so the total energy with respect to momentum. And there's a conjugate equation here. The time derivative of the momentum is the negative derivative of the Hamiltonian with respect to the model parameters. So just Hamilton's equations that probably many of you have seen before. Now, since we have H and we have P, we can actually solve Hamilton's equations numerically. And what we know from really simple considerations is that H, so the total energy of our space shuttle, is constant as it moves along a trajectory. So there's energy conservation in that system. So what does that mean? We have our total energy after some time t. So H, total energy, depends on the model at time t and the momentum at time t. And this is simply, as we've stated before, the sum of the potential energy at time t, which is equal to the misfit at time t, plus the kinetic energy at time t, which is again written here. Now, since energy is conserved, total energy is conserved, we know that the total energy after time t is equal to the initial total energy. And that initial total energy that we have here is equal to the initial potential energy plus the initial kinetic energy. Now we kick out a few terms, and then we see that potential energy at time t plus kinetic energy at time t is equal to potential energy at time 0. And then remember that we defined the initial momentum p hat just such that the initial kinetic energy is equal to that misfit tolerance that we defined at the beginning. Right? That was the misfit increase that we are willing to accept. Now, when you stare at this long enough, you notice that k of t, so the kinetic energy at some point in time t, is a positive quantity. Kinetic energy is a positive quantity, so the kinetic energy here is greater than 0. And as a consequence, we find that actually our misfit at time t, so the misfit of this other model at time t, is smaller or equal than the initial misfit plus the misfit tolerance. Right? So this is exactly what we wanted. What we see here is that all models m of t that are located somewhere along this Hamiltonian trajectory, they must produce misfits that we are willing to tolerate, right? Because they have a misfit that is smaller than the initial one, plus that little misfit tolerance. So in other words, all the models along that Hamiltonian trajectory, they're actually within the effective null space. So that's the way we construct those alternative models. Now let's navigate null space. Let's be a little bit more concrete. In the approach that I have shown you so far, we have a few variables that we can play with. So for example, the initial momentum or the direction of the initial momentum, but also the mass matrix, which so far was totally unspecified. And it turns out that depending on the different choices that you make, you can navigate null space in different ways, depending on what you would like, on which aspect of null space you would like to see. For example, we may have the interesting case where tolerance is actually 0. So that means our epsilon that we defined before, our misfit tolerance, is equal to 0. When you go through the analysis, then you find that in this case, this null space shuttle, so this computation of a Hamiltonian trajectory through null space, is actually exactly equivalent to a gradient descent method. So for example, to a steepest descent, to a conjugate gradient method, or to a Newton method. And the kind of gradient descent that you recover for this case of epsilon equals 0 just depends on your choice of a mass matrix. So basically, all the gradient descent methods that we know, they are special cases of the null space shuttle for different choices of the mass matrix, and a tolerance, a misfit tolerance that is equal to 0. Also, we may prescribe the takeoff direction. Right? So the misfit tolerance, this prescribes the absolute value of the initial momentum, but the initial direction is something that we are free to choose. And we can choose that direction, for example, in a way that allows us to add certain, for example, geological features to a model without destroying the fit to data. And also what we can do, unfortunately something I will not have the time to show, we can bias the null space shuttle such that it preferentially looks at rougher or at smoother parts of the null space. Let's look at some examples. The example that is here, that you see here, is a nonlinear travel time tomography. The setup is as follows. We have a domain that is 40 kilometers deep and 80 kilometers wide. And we have a few sources, say seismic sources, at the bottom, so at about 40 kilometer depth. And these are the ones that you see here as the gray dots. Now these waves, they emit, these sources, they emit waves that we model in the form of arrays, and they're being recorded at the receivers that are located near the surface. That's the setup. And what you see here in the background, this is actually a velocity model in kilometer per second. You see the color scale here to the right, that produces a misfit that we find acceptable. So it's already a good model. And now what we would like to do is we would like to add this kind of feature. We would like to add a blob to that model that we already find acceptable. So what we do for this, we define our initial momentum p hat to be equal to the blob. And then we let the Nullspace, the Nullspace shuttle fly through model space. So this is what this looks like. This is at time t equals 0. This is our initial model, and a model that we already find acceptable. And after t equals 4 seconds, these are artificial seconds, indeed we see that the blob has been added to the model without destroying the misfit. That the misfit has not been destroyed is what you see in the lower panel. In fact, here in this green dot at the beginning, at time t equals 0, this is the initial potential energy, that is the initial misfit. As time progresses, we see that the misfit increases. This is the green line here. Your misfit increases towards this model at time t equals 4 seconds. But we see that this misfit, by construction, remains below the total energy, below the Hamiltonian. So it is bounded by the tolerance that we added. And then, of course, we can continue. And then we see, as we progress in time, as time advances from, say, 0 to about 50, we see that the misfit, which is the green line or the potential energy, it oscillates between the initial misfit and the bound of the total energy. Sometimes it's a bit more, sometimes it's a bit less, but it's always below the blue line, meaning that it's always an acceptable model. Right? So here you see some snapshots. This is at 24 seconds, at 48 seconds. And then all of those models are acceptable. One can show this also in the form of a movie. So again, at the beginning, we add this blob, and then each of the alternative models that you see here in the movie is some position in this high-dimensional model space. And all of the models that you see are acceptable, meaning that they produce a misfit that is smaller than the initial misfit plus the tolerance that we have chosen. Now, instead of adding a blob, we can also add something that is random. That is what you see here. So we add a random model to the initially acceptable model, and also through this we obtain a series of alternative models along that Hamiltonian trajectory that we all find acceptable. Good, so this was the Hamiltonian Nullspace shuttle, which allows you to deterministically find alternative models that explain the observations to within our tolerance. Now we can go a little step further and turn this into a Monte Carlo method that actually samples the posterior distribution of our inverse problem. And the Monte Carlo method that is very closely linked to the Hamiltonian Nullspace shuttle is actually Hamiltonian Monte Carlo. So first, a little bit of motivation behind Hamiltonian Monte Carlo. It was originally developed in quantum mechanics already in the late 80s. It took quite some time because before it received some attention in geophysics. And it is a random walk method that allows us to sample, for example, the posterior probability distribution of an inverse problem. And the motivation actually comes from a very well-known deficiency of the Metropolis-Hastings algorithm, which you will see illustrated down here. When we execute the Metropolis-Hastings algorithm, we essentially have a choice between two extremes. The first one if we want to sample this probability density that you see here in gray, is to progress through model space in very small steps. The advantage of going in very small steps is that the acceptance rate is very high, meaning that literally every model that you propose is actually being accepted and turns into the next position of the random walker. But of course, the downside of this is that by going in very small steps, we explore model space very slowly. Now, the other extreme is that we go very big steps. Obviously, by going a big step, you make rapid progress through model space. But especially in high dimensions, making a big step also means that the likelihood of actually accepting that move is very, very small, because the likelihood of accidentally stepping into a part of model space that is plausible becomes extremely small. Right? So you need to find a balance between the two. Now, Hamiltonian Monte Carlo is motivated by this deficiency that you have to choose between those extremes. And in contrast to Metropolis Hastings and many other Monte Carlo methods, it takes advantage of derivative information. Taking advantage of derivative information allows it to make very long distance moves, but instead of having a very low probability of actually accepting that long distance move, the probability of accepting it is actually very high. And it is precisely this property that allows us to solve this kind of high dimensional problems that we are very often interested in geophysics. A conceptual introduction, you have already seen a little bit of the math in the previous section. So here it really just comes in pictures. We start with an initial model, in contrast to the Nullspace shuttle, that need not be a model that we already find acceptable. It can be randomly chosen. So this initial model is up here. And then we define the misfit as before as the potential energy of that initial model. We may again imagine the initial model in the form of a null space, of a space shuttle, and say we have a maximum likelihood model sitting somewhere that might be the Earth. So then what we do is we give that space shuttle or that model a random momentum. And as before, this is a purely auxiliary quantity. It's artificial. This random momentum defines the kinetic energy of the space shuttle. So, and then it starts flying, and it flies basically in our computer because we solve Hamilton's equations that gives us this Hamiltonian trajectory. So we fly from the initial position to some test model where we stop the trajectory. And we find this trajectory by solving Hamilton's equations. So we move to this new test model. Then we evaluate a modified Metropolis rule. It's not the same Metropolis rule as in the Metropolis Hastings algorithm. It's a little bit different. And based on the outcome of the Metropolis rule, the move to this test model is rejected, either rejected. In that case, we just move back to where we came from, or it's accepted. And in that case, we just continue and move on. So the same procedure, we draw a random momentum, the space shuttle flies somewhere, accept it or not, and then we continue. And then I think you see the pattern. We repeat this many, many times. So what are the key features of this procedure? The trajectories, they generally orbit around plausible models. Speaking in pictures, the Earth stays near the sun, or the space shuttle stays near the Earth. Right? So basically all the test models, they are through the potential energy attracted towards models that are actually plausible, and they're not allowed to escape into parts of model space that are totally implausible. This is also ultimately what allows the space shuttle to make very long distance moves towards models that are reasonable. And those long distance moves towards reasonable models, they are ultimately what enables a fast model space exploration. A perceived disadvantage could be that we actually require the derivatives of the forward problem, or more specifically, the derivative of the potential energy, which is the derivative of the misfit function. But actually, this disadvantage is very small because we can compute those derivatives very easily using adjoint techniques. A few ideas towards actual applications, and one that I want to show is a probabilistic full waveform inversion. It's a synthetic inversion. It's not a real data inversion. We are not there yet, but still I think it's promising. So what we did is we considered 2D elastic wave equation, and we solved that elastic wave equation in the time domain using a standard staggered grid finite difference method with a maximum frequency of 50 Hertz. And we consider 3 classes of model parameters: p velocity, Vp, s velocity, Vs, and mass density, rho. In total, we discretize our 2D domain using 10,800 grid points, multiplied by 3 different classes of model parameters means that our model space dimension is 32,400. As I said, we run a synthetic inversion as a proof of concept, basically to check if there's any hope that it will ever work with real data. So we define some target models that we use to compute artificial data. And shown here is the target S velocity model on top. So here Vs in meter per second, and below a target density model. And then what we do is we run this Hamiltonian Monte Carlo sampling, and based on this collection of samples, we can compute various statistics or various properties of the posterior distribution. For example, the mean Vs model, which you see here, or the mean density model. And you see that they actually somewhat closely resemble the target models that we used in the beginning in order to generate artificial data. But of course, you can also do some sort of uncertainty quantifications, and one of the quantities that one may want to compute, and possibly in addition to many others, are the standard deviations of those model parameters. And this is what we see here. So the standard deviations of S velocity, and below the standard deviations of density. Good, so a short summary of what happened here. What we basically get, thanks to this Hamiltonian Monte Carlo sampling, are parameter estimates, including uncertainties. What is interesting here is that we actually, I wouldn't say constrain, but that we obtain information about the distribution of density, which is traditionally in seismic imaging is extremely hard to get. And we get this estimate of density, including the uncertainties, without actually injecting any subjective regularization. So it really just naturally comes out of the sampling. That brings me to the last part of this talk, which is on auto-tuning. So this Hamiltonian Monte Carlo method that I talked about, but also the Hamiltonian Nullspace shuttle, they have tuning parameters. And by far the most significant tuning parameter is the mass matrix. So this mass matrix, if you will, is the mass of this Nullspace shuttle. And the mass matrix is by definition a positive definite matrix. It needs to be positive definite because you need a positive kinetic energy. And it is symmetric, and it has dimension of model space dimension squared. Okay, so just to give you some idea, if our model space dimension is 1000, then the dimension of the mass matrix is 1000 by 1000, meaning that it has 1 million entries. Since it's symmetric, only about half of them are independent. So you have roughly 500,000 entries in the mass matrix. And that means that the Hamiltonian Monte Carlo sampler has 500,000 tuning parameters. I think it's clear that 500,000 tuning parameters is not something that you can do by hand. This is somewhat unfortunate because the tuning of this method is what can potentially make it very efficient and more efficient than other methods. But on the other hand, if you don't tune, the method may be hopelessly inefficient. So you need some mechanism to find suitable entries of the mass matrix. And this is what this chapter is essentially about. Now, what is actually behind it is the actual challenge of drawing independent models. What does it mean, drawing independent models? It simply means that the random walker goes from one position in model space to another one. And of course, what you would like the random walker to do is to see models that are actually different from each other. And so you don't want to go a large number of steps, and in the end, all of the steps or all of the models that correspond to those steps look kind of similar. And then you haven't learned anything about your model space or about the null space. You want the random walker to be able to go towards independent models using as few steps as possible. This is important intuitively because it enables efficient model or null space exploration. If your models are independent, you see many different corners of null space or of model space. Whereas when they're all similar, so when they're dependent, then you're essentially always seeing the same corner of model space. But also from a mathematical perspective, we know that Monte Carlo integrals, so for example, the computation of a mean, of a variance, or the computation of a 1D or 2D marginal distribution, have a convergence speed that is proportional to 1 divided by the square root of the number of independent samples. Right? So if your samples are all very dependent, then the number of independent samples is very small. And so your Monte Carlo integration converges very slowly. So you want to have as many independent models produced by a certain number of steps of the random walker. To illustrate this, let's look at an example. The example may appear boring, but it's actually quite instructive. It's the sampling of a 1000 dimensional Gaussian. Now, a Gaussian itself is a boring creature, but actually looking at it in 1000 dimensions becomes non-trivial. Now, this Gaussian has a covariance matrix that is diagonal, and those diagonal entries, they range from C11 equals 0.1 to C1000, 1000 equals 1.1. And so the diagonal entries of this covariance matrix vary by about an order of magnitude. And initially, we run this Hamiltonian Monte Carlo or the null space sampling using a mass matrix M that is equal to the unit matrix. And then what we want to do is we want to measure how dependent or how independent successive models in this Monte Carlo chain actually are. There are many ways of measuring dependence or measuring independence. What we will do is we will compute the autocorrelation of the chain of samples. So we produce a chain of samples, M1, M2, and so on and so forth, depending on where the random walker is going. And then we compute the correlation function of the chain of samples. And this is what you see here. So what I did, I sampled this 1000 dimensional Gaussian with covariance entries or covariance entries varying by an order of magnitude. And first, let's look at the autocorrelation of this model parameter M1000. This is the red line. And there we see that after making, I'll say about 50 steps, which may be here, the models that we see have become independent. So the random walker, so this Hamiltonian Monte Carlo random walker, makes 50 steps. And after about 50 steps, he starts seeing models that are significantly different from the models that he has seen before. But for the other component of my model vector, M1, this looks very different. No matter how many steps I go, the samples that I see, or the corners of model space that I see, are all very similar to what I have seen before, simply because that autocorrelation remains close to values of about 1 or say 1 or 0.5, meaning that even when I go many, many steps, say 1,000 steps, for example, I still see models that are highly correlated to the models that I have seen a long time before. So in the direction of M1, model space exploration is extremely inefficient, whereas in the direction of M1000, it is very efficient. Now we can understand actually what's going on by looking at the trajectory of the space shuttle, to this Hamiltonian trajectory of that point flying through model space. Plotted in red is actually that case that we just considered, namely that the mass matrix is equal to the unit matrix. And there you see in this projection, so here is model parameter M1, model parameter M1000. And you see that in this 2D projection, the space shuttle flies very rapidly in the direction of M1000, but it makes very slow progress in the orthogonal direction M1. Right? So it takes a long time along that trajectory until you actually see a different part of model space in coordinate direction M1, whereas in coordinate direction M1000, the space shuttle is a lot faster. And what we would like to do is we would like to homogenize this. We would like the space shuttle to progress with equal speed in all coordinate directions. And you can show analytically, in the case of a Gaussian, that you achieve this by choosing your mass matrix to be equal to the inverse covariance matrix. If we choose this mass matrix, then our Hamiltonian trajectory actually becomes the blue curve, and that blue curve indeed makes equally fast progress in M1000 direction as in M1 direction. So this is nice and good. We know that the ideal mass matrix is the inverse covariance matrix, which happens to be the Hessian of the misfit function. The problem, of course, is that the Hessian, for any problem that we are realistically interested in, can neither be computed nor stored explicitly. It's just too big. So what autotuning does, it actually approximates the Hessian on the fly. So what we do is we use the last couple of samples to approximate the Hessian vector product. And that's actually all we need in the algorithm. At no place in the algorithm do we need the Hessian explicitly. We only need Hessian vector products. And we approximate this using a couple of samples. And so basically imagine that the random walker walks through model space, makes a certain number of steps, say 10 steps. And with those 10 steps, the random walker samples a certain neighborhood of model space. And on the basis of what the random walker has seen during those 10 steps, he actually approximates the local curvature of that region. Right? And that translates into approximating this Hessian vector product. What we effectively do is we run a variant of the so-called LBFGS method. So this is the limited memory variant of the BFGS method, which is very well known from nonlinear optimization. And we basically borrowed the method. We translated from deterministic nonlinear optimization to random Monte Carlo sampling. Instead of using deterministic steps as a nonlinear optimization, we use the random steps of the random walker. And then what we do is we use this approximation of the Hessian that we get through LBFGS as a mass matrix that then enters the computation of Hamiltonian trajectories. So does this work? Coming back to our example that we have seen before, here this auto-tuning based on LBFGS is turned off. We have seen this before, so that one of the model parameters M1000 decorrelates very quickly, whereas M1, plotted in black, stays correlated for a very long time. Now we switch on the auto-tuning, and then this autocorrelation plot looks like this. Right, so as before, model parameter M1000 decorrelates quickly, but also model parameter M1, again plotted in black, decorrelates equally fast. And so now, instead of requiring thousands of steps in order to see something different, the random walker only requires about 25 steps in order to see a significantly different part of model space. Now, this is the Gaussian. The Gaussian, as I said, is kind of boring, but it's a good proof of concept. It teaches us something about the mechanics of the whole problem. What is a lot more fascinating, however, is the so-called Stiplinsky Tang function. In 1000 dimensions, the Stiplinsky Stiblinsky-Tang function has 4 to the power of 500 local minima. So it has an enormously large number of local minima. We can't plot the 1000 dimensional function, but we can plot a 2-dimensional projection. And this is what you see here. So again, I picked out model space directions M1 and M1000. And there you actually see 4 of those 4 to the power of 500 local minima. And then we run this Hamiltonian Monte Carlo in order to sample that 1000 dimensional function. Again, we start with the case where the auto-tuning is turned off. So we use the identity matrix as mass matrix. And there again, we see that one of the model parameters, M1000, decorrelates quickly. So you quickly see different parts of model space. But again, our problem child M1 remains correlated for a very long time, meaning that you need a very large number of samples before you see something else in M1 direction. And then we switch on the auto-tuning. And again, the picture changes dramatically. And also our model parameter M1 decorrelates quickly after about 20, 25 samples and starts seeing different parts of model space. This, of course, also translates into our sampling of the posterior. What you see here is a projection of this 1000 dimensional function onto, again, M1 and M1000, sampled by this Hamiltonian Monte Carlo sampler. When the auto-tuning is turned on, so when we efficiently see independent models, then indeed we manage to see all of those 4 projected local minima. However, when the auto-tuning is turned off, we actually miss one of those local minima. Right? So this is not being discovered. The random walker does not manage to see models that are sufficiently independent to actually also discover the local minimum that is at that position. Good, some conclusions. First, we have seen those Hamiltonian null space shuttles, which are a pretty efficient way of exploring the effective null space of nonlinear inverse problems. Of course, it can also be used for linear inverse problems, but that would be an overkill. What it enables is also quantitative hypothesis testing and the targeted construction of alternative models. The randomized version of those Hamiltonian null space shuttles are actually the Hamiltonian Monte Carlo method, which has been known actually long before people thought about null space shuttles. It's a randomized version, and what we see, for example, in 2D full waveform inversion, is that we can handle problems with order of magnitude 10,000 model parameters. And note here that this was done without any supercomputing. So what you saw there actually was running on a laptop. And based on this, we think that a probabilistic full waveform inversion in 3D is actually within reach. Not at very high frequency, but at least the proof of concept, I think, is something that will become possible within the next few years. Then this auto-tuning allows us to find a very efficient mass matrix, and it combines classical Hamiltonian Monte Carlo sampling with a factorized version of the LBFGS method that we borrowed from deterministic nonlinear optimization. What it allows us to do is rapidly generate independent models and thereby also improve convergence of Monte Carlo integration. And I really think it holds great promise for realistic applications. If you want to know more, there are a few applications, a few publications. The first 3 are already out. The 4th one is under review. It's about this auto-tuning method. If you would like to know more, I would be happy to share that even before it's published. That's all I wanted to say. Thanks for your attention. I would be happy to answer questions.
Thanks very much, Andreas. Is there any question or comment for Andreas? I haven't seen anything.
I have a question here, Yao. Andreas, thanks for a very interesting lecture. I got a question about the first part, the Hamiltonian null space shuttle.
Mm-hmm.
I'm looking at if I interpret the P as a model perturbation vector, and then m-1 as a regularization matrix, then that formulation is actually got a parallel interpretation in a classical Fichtner regularization form. Then that formulation is actually equivalent to looking for a model perturbation that actually leads to the increase of the data misfit epsilon.
Mm-hmm.
So I find it really interesting, striking that you have this different interpretation. I just want if you have comments on that connection.
To be honest, I had not really thought about that connection. So I will need to dig into that a little bit more.
Okay, cool. Basically, that to me, I could be totally wrong, but that's almost like a formulation with the existing model you have. Then you do use that reference model to look for a new model, but regularization is applied not to the final model, but perturbation.
To the perturbation, exactly.
Yeah.
Yes. Yes.
Cool.
Yes, and you could use it as regularization if you want to. So you can use the mass matrix to regularize in the sense of trying to find models that are smoother. Okay? But it's not only that. You can actually also use it in the opposite direction. You can also use it to find models that are rougher.
Thanks.
So it can act as a regularizer, but it does not have to.
Yeah, this rule. Nice talk, Andreas. I think I missed a few jokes. But I have if you have a model with let's say just two values, right, in one dimension, then with an energy barrier in between, you will never get over the energy barrier.
So you're right with the deterministic Nullspace shuttle.
Right.
You will not get across the barrier unless you set your tolerance high enough. For the Hamiltonian Monte Carlo, you will eventually get across the barrier.
But my question is, why stick to a Hamiltonian method? Why not kick it off with a higher energy and then look at the development of trajectories when you include some dissipation?
Oh, okay.
Because then you can basically say, hey, you can go into well number 1 or well number 2, whatever you like. But ultimately, I'd like you to settle down to a certain level.
Yeah.
That must be easy to code up with all the.
But the dissipation, will the dissipation really get you?
Well, you're going to lose energy, so you cannot stay at the barrier. You're gonna go to either the one valley or the other valley. I mean, it's just.
But I think dissipation will in the end lead to the space shuttle being stuck. So what it will do, it will essentially. Well, I think it's predictable what it will do. It will be equivalent to a local descent method, right? Because in the end, you will dissipate all the kinetic energy, meaning that you will end up at the local minimum.
No, but you can switch off the dissipation once you reach your value of epsilon. You say, okay.
Oh yes, absolutely. So you could use it initially in order to go to models that you like more. And then switch on dissipation to sample that region more. Yes, absolutely.
I mean, that must be a pretty simple extension of the current algorithms, I would imagine.
Yes.
Without major surgery.
Yes, I think so.
I mean, there may be other methods, but
yeah. No, I totally agree. Yes.
Any question for Andreas? Students specifically.
Can I ask one, although I don't belong to the department?
Yes, please, Ganesh.
Okay, yeah. Oh, it's very, very nice talk. It's highly mathematical as well. Just something small to start with. I think the use of the term null space is not mathematically robust, right? You just used it more like a shuttle thing.
I agree.
It's not clear to me what a null space or what it is, null space of what operator, what subspace and so on. It's more of a fancy word to use it, I suppose. Yeah.
Yes, I totally agree that it's not a perfectly precise mathematical definition. You're right.
Okay, great. I think the use of Hamiltonian is a very interesting idea to move a little bit further than Monte Carlo and for other variants like quasi-Monte Carlo and so on. But for the UQ part, for the inverse, I don't see how using Bayesian with, let's say, Gibbs sampling will be less efficient than what you're proposing. I think yours might be more expensive.
So to be honest, I have never seen a Gibbs sampler working for a geophysical application.
Yeah, okay. Because you kind of took a
reasonably high
efficiency for metropolis Hastings, right?
So I mean, what I can tell you, I mean you can see Gibbs as a special form of metropolis Hastings, right?
Yeah,
so
okay.
Now the crux here is that you can actually estimate the number of samples that you need in order to, in order to produce an independent sample. Okay.
Mm-hmm.
So, and you can actually show that for metropolis Hastings, this number of samples scales as model space dimension squared. Okay, so basically means as your model space dimension increases slightly, you need many more samples before a sample actually becomes independent. Now for HMC, this is n to the power of 5. Wait, I think it's 4/3. Right.
That's provided you take mass matrix to be sparse, right?
That has nothing to do with the mass matrix.
Okay.
The mass matrix can actually be dense, and in fact, in the LBFGS approximation, it's actually dense.
Okay.
So that means with HMC, your scaling with increasing model space dimension is a lot better than for metropolis Hastings, and that's the main reason for using it for problems that are relatively high dimension. When dimension is low, it's an overkill and it's just more expensive. You're right.
Okay. Yeah. I mean, oh yes, I agree with that. If it's more than 10,000, 20,000,
yeah,
but it's harder. I think that's where this might be helpful.
Yeah. So HMC really becomes beneficial when model space dimension increases.
Is extremely okay. I think it'll be good to have some good comparison. For example, Gibbs sampling gives marginal posterior easily, right?
Yeah. The thing is, we've been asked this by reviewers, for example. The problem is that you're always comparing apples and oranges.
Right.
It's so basically, if you will, the no free lunch theorem precludes from the beginning that such a comparison can be objective. Yeah. And so you will always be able to find, or say, to construct a problem where metropolis Hastings is vastly more efficient, and you will also always be able to find a problem where HMC is vastly more efficient.
Right.
So that's a general difficulty, I would say.
Okay.
We know that it works for certain applications,
yeah,
but we can't immediately extrapolate that.
Thanks. I think you explained it very well. This is really hard to compare because on the face of it, it's clear that Hamiltonian solves together, although you can do adjoints and so on. It is expensive, but on the other hand, property-wise, this is much more robust in many ways in decorrelating, as opposed to the standard Bayesian with even any metropolis. I mean, of course, there you have a kind of good advantage of this likelihood, very well defined.
Yes.
I mean, I see your title of the paper. Maybe I'll look into that. I mean, in your Bayesian, you will also define the likelihood similarly, right? Nothing changes, right? Mm-hmm. When you do that, so everything is similar except that you're sampling it differently. And
exactly.
I see.
You're making proposals differently.
Okay, I see. Okay.
And the metropolis rule looks a little bit different.
All right, thank you. And is is this code available? I mean, that sense of, Metropolis are available.
If you go to our website, it's www.swp.ethz.ch, and when you go there, we have a sub website with scientific code, and there we have example codes of HMC.
Okay, I see.
In Jupyter notebooks that you can play with.
Okay, I see. Because in ETH, I used to be in ETH visiting prof and so on with at Sam. So I mean, those guys will ask these similar questions, right? They do this QMC and Chris Schwab's and Ralph and stuff like that. So I think there'll be a lot of interest. I think this is very good, actually. I'm quite impressed. I'm planning to look into that carefully. Thank you very much.
Thank you.
Any other question? Well, if there is no other question, I would like to thank Andreas you one more time
also, thanks again
for giving this lecture at midnight, and I don't want to hold you or keep you awake further. So thanks very much for joining us, and
yeah, also thanks again for the opportunity, and thanks for listening.
Of course. Have a good night.
Good night. Bye-bye.
Bye-bye.